Shall we start? So do I need to wait more or shall we start? So today the discussion is basically on bipolar junction transistors, BJT. So we have different type of transistors, like one is very simple, one is BJT. So other than that, we have field effective transistors, MOSFETs and so on. There are a lot of different types or different varieties of transistors. So during this analog electronics one, we basically go through this BJT, which is the very simple transistor. So the bipolar junction transistor. So in this bipolar junction transistors, basically this majority and minority carriers are contributing to the operation of this transistor. So that's why we define those elements as bipolar. So both majority and minority carriers are supporting to deliver current. So the entire operation is basically depend on this majority and minority carriers. So if you go into details, so we can discuss how this majority and minority carriers are affecting to generate these currents and so on. So believing that this during this physical electronics module, you basically covered this fundamentals of BJT, how do we construct this PN, PO, PN transistors, and the properties of this BJTs and so on. So the physical construction of this BJT is basically covered in physical electronic, I guess. So here we basically focus on implementing circuits and analyzing these circuits using what the well-known Kirchhoff formulas and so on. And how do we predict the output and how do we analyze the circuit, how the behavior is up, and if you change the parameters, what happens to the circuits and so. So this kind of a discussion is basically carried out during this couple of sessions. So we may not go into that much of details of this physical construction of these transistors, but we focus on the circuit level analysis of these BJTs. So you may aware that so we have two types of BJTs, bipolar junction transistors. So one model is this PNP type, the other one is like NPN type. So the difference here is like so we have so two PN junctions. So the diode basically has a single PN junction, but in this case we have two PN junctions. So with these two PN junctions, so we can basically develop a three-terminal device. So this is like a three-terminal device. So three-terminal device. So we can define those terminals. So this is like emitter. So this is base and this is collector. Similarly, this is E. So these terminals are basically known as emitter, collector, and base. So these both emitter and collector come from the same semiconductor material, so either P-type or N-type. So we basically differentiate this emitter from collector by increasing the doping level. So the emitter has a higher doping concentration compared to the collector to generate this more free of electrons or holes. So this is the simple difference between the emitter and collector. So they are basically same semiconductor material, but with a different doping concentration or doping rate. So base is the common layer for these two semiconductors. If it is a PNP, so the N layer is the base. So this N layer acts as a kind of a common interface for these two PN junctions. So if it is an NPN type, the P layer is the base, and it basically acts as a common medium for this both N type semiconductor materials. So here, by looking at this one, so if we go to the diode, so we have this diode. So similarly, so this is your P and N layers. So this is the diode. So if you go for this material level, we have P and N type layers merged together and build the diode. Similarly, for this BJT, we have two PN junctions. So this is one PN junction. If it is a PNP, so this is one PN junction. So the other one is this one. Similarly, for NPN, this is one junction. The other one is. So you have PN block. So which is basically providing this diode operation. So here we have another PN block. Similarly, PN two PN junctions are there. So then by looking at the semiconductor arrangement, we can model this transistor using a kind of a dual diode model. So dual diode model. So in this dual diode model, what we can simply do is we can replace this PN junctions using diodes. So for example, if we consider this block, so we have PN junction here. So what we can do is we can simply draw PN junction. So this is the positive terminal of the PN junction and this is the negative terminal. Similarly, we have another PN junction here, so which is basically to the other way around. So we can draw like this. So this common point is tag them out as a base, and this is basically collector, and this is basically emitter. So if you consider the NPN type, so it's something like that. For the PNP type, so we have, in both cases, we have two diodes which are back-to-back connected in this PNP type. So we basically connect these negative terminals back-to-back. And if it is an NPN type, we connect these positive terminals back-to-back and get a diode. So now these transistors, these bipolar junction transistors or BJTs, so which are basically divided into two categories, PN, PN, and PN. So based on this PN junction arrangement, we can model these transistors as dual diode devices. So then, so the entire discussion is then focused again to these diode operations. So we convert these transistors to a kind of a diode model. So then you have kind of a comprehensive idea about how these diodes are operating. So using this knowledge, we try to understand the operation of this BJT using this dual diode model. So then we don't have any transistors anymore. So we have circuits contain multiple diodes, so you can think of how those diodes are operate inside a circuit rather going to a deep analysis of transistors. So yes, okay, maybe due to this poor internet connectivity, sorry for that. Yes. So then we can have this symbolic arrangement for these two types of diodes. So if it is a PNP type, so it's something like that. So we have base, so this is a base, emitter, collector, collector. So the arrow represents the direction of the current flow. So this is your PNP type. So this is actually NPN type. So in this NPN type, so you have this arrow which is basically come out from this block, and this PNP type, so the arrow is towards the north. So it basically represents the direction of the current. So it means like, so this is the direction of this current. So IE, this is IB, and this is IC. Similarly, this is IB, IC, and IB. Okay. So for this transistor operation, we basically discuss two types of analysis. So one is actually called DC analysis. So the second one is called the AC analysis. So why we have these two types of analysis actually? So you may aware that transistors are basically used to implement amplifiers. So amplifier is a kind of arrangement. You can boost your input signal up to a certain level, or else you can have a gain between output and input. So it means like it's a kind of like, for example, audio amplifier. So whatever the input of a mic would be amplified and feed it to a kind of a speaker. So then audio input is a kind of a time varying input. So it's depend on the vocal properties of that. So the whatever the induced voltage is having a kind of a time varying function. So it's something like time varying function. So this is your audio input and it's fed to the amplifier, and you can basically get a kind of an amplified version. So then this particular device basically manage alternative type of or time varying currents and voltages. At the same time, to operate this transistor to the way which we want, we need to make this transistor in a particular level. So we have to set certain parameters to operate this transistor as what we want. So this is called like biasing of the circuit. So to make this biasing process for the transistor, we need to do some analysis part, which basically concentrated on DC components only, DC currents, DC voltages, and based on this DC voltages and current, we can find out the resistors which we need to place on these terminals and the rest of the circuit. So this is basically called DC analysis. So why we need DC analysis is to make your transistor to work at a particular level what we want. So if it is amplifier, we need to amplify the circuit. So then initially we need to place the transistor to work at particular point. So to bring this transistor to this workable model, we need to have this biasing. So with this biasing, we basically manage all these DC quantities in the circuit and find out whether we can place the transistor to that particular operating point. So this process basically do this DC analysis part. In addition, on top of this DC analysis part, so we can bring this external time varying inputs to the system and make it amplified and send it to the output. So then on top of this DC signal, we may basically feed time varying quantities to this circuits. So then we can have a separate analysis for this AC or time varying signals. What would be the gains and impedance for this AC signals and so on. So then during this couple of sessions, we basically concentrated on this DC analysis of the transistor as well as the AC analysis of the transistor. So it means like for DC analysis, we are focusing on DC quantities only. For AC analysis, we basically concentrate on AC quantities. So then first of all, we need to differentiate these AC quantities or AC parameters and DC parameters. So how do we differentiate? If you basically use this capital letters, V, I, so it means we basically capital letters with capital subscript. So they basically represent the DC quantities. So these are DC quantities, DC values. So if you basically use capital letters with capital subscript, so those are basically so this capital letters with capital subscripts, capital letters with capital subscript basically indicate the DC values. It may be a voltage if you put V, if it may be a current if you put capital I. So this subscript basically indicate which point you are referring. For example, so we have three terminals. One is this emitter, then collector, base. So we use this capital E to indicate the emitter, capital B to indicate the base, capital C to indicate the collector. So if it is a like for example V, a subscript E, capital E, represent the voltage at emitter. So this is basically voltage at emitter. So likewise, this capital IB represent the base current or the current flow through the node B or this, yeah. So these are DC quantities. So this is a kind of a DC voltage at the emitter. So this is the DC current flow through the node base. So likewise, we can define multiple parameters for this network. So this is like if this is your voltage at emitter. So this is voltage at base. This is voltage at collector. So if you indicate like this, so this is voltage at base with respect to emitter. So this is DC voltage at base with respect to emitter. So if you indicate like this, so this is voltage at collector with respect to emitter. So these arrows represent the DC current flow through the terminal. So IE represent the current flow through the emitter terminal, DC current. IC and IB are basically representing this collector current and the base current. So likewise, you can define like multiple parameters by looking at this configuration. So we have different set of parameters like VE, VB, VC, IB, IC, IE. So then VBE, voltage at base with respect to emitter, voltage at collector with respect to emitter, voltage at base with respect to collector, and so on. So you can basically define so many parameters, so many voltages and current by looking at the configuration. So you can evaluate those values if you basically need to design a circuit. So you can easily find out the node voltages, node currents, as well as the voltage with respect to the other nodes as well, like this. So what I want to highlight at this point is like one, so we can simply convert this PNP or NPN transistors to a kind of a dual diode model. So then rather going into detail of this PNP or NPN transistors, we can brief out, we can explain the circuits using this diode arrangement. So this is basically more than enough to understand the behavior of this transistor circuit. So use this dual diode model and replace the PNP or NPN transistor and see what happens to the circuit by looking at the diode perspective. So this is the first thing I need to highlight here. So the second is actually depending on the transistor configuration, we can basically identify different set of parameters. Some may be AC related quantities, some may be DC related quantities, because for these transistors, we later on deal with both AC and DC quantities. And then we have two separate analysis for DC quantities and AC quantities. So that's why we need to differentiate this AC and DC quantities separately. So if you are dealing with DC quantities, those should be capital letters. Whatever the parameters quantities you are looking should be in capital. So V for voltages, I for current, and then you can introduce a corresponding subscript according to your requirement. If it is like V subscript E, it basically represents the voltage at emitter, DC voltage at emitter. Similarly, if it is a kind of a VBE, so it's the DC voltage at base with respect to emitter. For this kind of cases, so VBE actually equals to VB minus VB. So this is a very simple relationship. You may study it in the circuit analysis 1 as well. So if you are asked to evaluate the voltage at base with respect to emitter, you can simply uh, take the voltages at B, base and emitter, and if you just subtract these two quantities, give the voltage at base with respect to emitter. Likewise, VC minus VE gives the voltage at collector with respect to emitter. So the rest of the parameters or the currents are straightforward and you can easily derive those values. And from here, so we can make a simple relationship. If you assume that transistor is a kind of a node, so if you assume that transistor is a kind of a node, so then this, if it is a node, so this is a transistor as a node. So then we can apply Kirchhoff current law and can come to a conclusion that the emitter current is basically equals to collector current plus the base current. If you assume that transistor is a kind of a small node, which basically consider in the circuit analysis, we can apply Kirchhoff current law and come to a conclusion that the current flow through the emitter terminal is exactly equals to the sum of the current flow through the collector and base. So this is one equation we can use in many cases when you are dealing with transistors. So this may be useful when you are evaluating this voltages with respect to some other nodes. So these are the important points, so which I need to highlight in the very introductory slide. So then we'll move to this transistor arrangement. So if you have any questions, just ask or just drop a message to the chat box. Yes. So the next is actually so if you basically want to make this transistor active, so we need to satisfy these two conditions. One is you have to make this base emitter junction forward bias, and the other one is like base collector junction reverse bias. So these conditions should be satisfied. So if you want to make your transistor as a kind of active device, so we need to maintain these two conditions. One is like base emitter junction should be forward bias and base collector junction should be a reverse bias. So how do you maintain this? So let's take a simple example. So this is your NPN transistor. So you have NPN transistor. So you'll take this is emitter, this is collector, this is base. So what's your base emitter junction? So this is the base emitter junction. So this is your base emitter junction. And this is the base collector junction. So you want to make this junction forward bias. So you want to make this base emitter junction forward bias and this junction reverse bias. So how do you do it? So we have, if you replace this transistor PN junction arrangement using diodes, so you can think of like this. So we have a diode like this, and here you have a diode like this. Okay, so if you want to make this base emitter junction forward bias, which means you need to make this diode forward bias, because now we replace the transistor operation using a dual diode module. So if you want to make this base emitter junction forward bias, so there's a junction diode. So it's something like that. So the orientation is like this. So you want to make this diode forward bias, then you can claim that this base emitter junction is forward bias. How do you maintain this junction to make it forward bias? So from the very basics we studied for diode, so you can simply say that. So this is the P or the positive terminal of this diode. So then if you apply a positive voltage to here and negative voltage to here, definitely, so this diode becomes forward bias. Then this, ideally this base emitter junction would be forward bias. Similarly, if you connect a source like this, and this is again another PN junction which we can simply replace, which we basically can replace with another diode. So if you want to make this reverse bias, so this is the positive terminal of the diode. So once you connect a negative potential to this one, so then ideally you can see like through this two separate voltages VEE and VCC, you can basically manage these two conditions to make your base emitter junction forward pass and base collector junction reverse pass. So for this particular case, we need to have two sources. So one is VCC, the other one is VEE. But if you consider a practical circuit, so you need to feed these two junctions through a single power supply. So later on we can see how we can accommodate these two conditions using a single power supply. So for the time being, keep in mind, so these two conditions should be satisfied. So once you plan to use a transistor, so you have to make this transistor base emitter junction forward bias and base collector junction reverse bias. So in that manner, you can plug your external DC sources to the transistor, then your transistor become an active element. So this is the other very important information which I need to share with you. So if you want your transistor to be an active element, you have to make sure that your base emitter junction is forward bias and base collector junction is reverse bias. Okay, then. Okay. So it means like, for example, let's think of like we don't have this source. For the time being, let's assume that this source is not there. So if you make this base emitter junction forward bias, so you can see a kind of a current flow through this one. You can see a current flow through this one. Because you make this base emitter junction forward bias, we know that if the diode get forward bias, there should be a current flow due to this majority carriers. Similarly, if you apply this other source and drop this from the network, so this base collector junction is now reverse bias. So then you can't see any kind of a notable current flow through the device because this junction diode is basically reverse bias. But from this physical electronics, you may aware that whether this minority carry, so whether these majority carriers are not contributing to the current. So if it is reverse bias, there should be like a very small current flow due to these minority carriers. So then you can simply say that there's a minority carrier flow through this other PN junction, which is actually reverse bias. Okay. So then if you connect these two sources together, so you can basically have this two currents. One is due to this majority carriers, the other one is due to this minority carriers. So then the whatever the contribution coming from this both majority and minority carriers are basically flow through this emitter. So the current flow through the emitter would be the majority carrier flow due to this base emitter, forward bias base emitter junction, and the minority carrier flow due to this reverse bias base collector junction. So this is the way we can make this diode active. So if you manage to maintain these two conditions, so you can basically make your transistor active. So I'll go through this slide set as a kind of a summary. So not going into detail. So believing that this BJT1, BJT2 slide sets are already shared among yourself. So I send it to Dilanka. So assuming that he basically shared the slide set with you. And the next thing, so initially we found that this, if you assume that the transistor is a kind of a node, we can claim that this equation is correct. So by applying Kirchhoff current law, so the emitter current is equals to the sum of this base and collector current. So, and at the same time, if you carefully observe this one, so these are basically in milliampere range. So this is milliampere, and this is also in milliampere range, and this base current is in microampere range. So this the magnitudes, by considering these magnitudes of IE, IC, IB, we can claim that IE is actually almost equals to IC, considering that this base current is very, very small, because it's in microampere range, so a couple of microamperes. So the contribution of this base current would be very mild to this emitter. So then we can basically assume that the emitter current and collector currents are almost in same dimension, because the base current is in microampere, so the rest of the currents are in milliampere range. So this is one approximation you can consider if you want to analyze a circuit. For example, if this base current is known, or if you are not in a position to evaluate this base current, so you can stick into this assumption by simply saying that base current is in microampere range, and you can neglect the contribution and come to a conclusion like IE equals to IC. So it's basically you can use this approximation if you can't evaluate the base current precisely. So if you have enough information to evaluate or determine this base current, so you can't use this one. If you want to simplify the version, so then you should clearly mention that based on this assumption, you basically take IE equals to IC. So without that assumption, you cannot simply claim that IE equals IC. So if you want to simplify the question, you have to precisely mention that I am neglecting this base current. So otherwise, whatever the calculations you uh, brought into the picture may not be valid without that assumption. So if you are in a position to evaluate those base currents, so the wise way of continuing is use this fundamental equation, this. not this approximation. And again, here we can define the parameter called DC current gain. So we use this beta, or in some cases use this HFE. So this is IC divided by IP. If you take the ratio of DC currents flow through the collector and base, so it gives the DC current gain. So sometimes it's like beta DC or beta, or in some reference they use HFE as the DC current gain, which is the ratio between the collector current and the base current. So from this you can get a nice relationship. IC equals beta times IB. Similarly, you can take the value for IB as 1 over beta times IC. So these two expressions are valid. If you know the beta value or the DC current gain, you can easily get it from the data sheet of your transistor. So it's mentioned that whether it's 50, 100, 150, 120, or sometimes maybe in between a certain range, 120 to 150, because these parameters, especially this beta or the DC current gain, is highly influenced by the temperature variations. So then most of the data sheets, it basically gives the HFE or this beta value as a range. For example, in between 120 to 150. So if you refer the data sheet, sometimes you can find out the exact HFE or beta by looking at the graph they embedded in the data sheet for certain cases. So they may discuss this HFE with the temperature T. So then you can think of like the operating temperature of the circuit, and based on that you can simply pick the exact HFE, or else you can simply think of a kind of a middle value like 130 for the safe side. So if you want to go for a precise analysis, you have to use this plot which is given in the data sheet, and you get the exact HFE or the DC current gain for the analysis. Otherwise, you can select a kind of a nominal value in between that range, representing this overall performance. Or else most of the questions, this HFE is a kind of a fixed constant value like 100 or 130. So in the analysis questions, most of the time it will give us a kind of a one value, not a range. So then the analysis would be pretty much easy then. So here we basically identify this Kirchhoff current law equation. So then this DC current gain plus the equations we built to show the relationship between IC and IB. So we basically have two equations. One is like IE equals IC plus IB. So the second one is IC equals beta times IB. So if you combine these two together, so you can simply say that IE equals IC actually beta times IB plus IB. So then IE is actually 1 plus beta times IB. So this relationship can be easily obtained from this previous equation. So those are valid if you have these quantities in your hand. So from this, from this you can basically find out the collector current if you know the base current and the DC current gain. If you know the collector current and base current, you can easily evaluate the emitter current as well. Okay, so this is the way you can move forward with non-base current. Okay, so then we found that this transistor basically has three terminals: base, collector, and emitter. So then we can organize this transistor in three different ways. So you can basically organize this transistor in three different ways. So one is this way. So the simple difference between these three orientations or the configuration is here, by looking at this one, for this case, so this base is common for this left hand side and the right hand side. So this is common base. So for this case, you can easily identify that this emitter is common for this block and this block. So this becomes common emitter. So the last one, common collector. So here this collector is basically common for this both sides. Okay. So for this case, we can identify, so the left hand side of the circuit, so we consider this is as your input circuit. So the right hand side basically your output circuit. This is your input circuit. This is your output circuit. Input circuit, output circuit. So for this first case, your emitter base junction is your input circuit. Emitter base junction is your input circuit, and the base collector junction is your output circuit. For the common emitter configuration, your input circuit is basically base emitter junction, and your output circuit is basically collector emitter junction. Similarly, for the common collector configuration, so the base collector junction is your input circuit and collector emitter junction is your output circuit. So then by looking at these three different configurations, we can easily found that so one of the terminal is common for both input circuit and output circuit. For the first case, it's a base, so then we define this configuration as a common base configuration. If your emitter is basically common for the both input circuit and the output circuit, so we define it as a common emitter configuration. If your collector is basically common for the both input and output circuit, So then it becomes a common collector configuration. So then by changing the terminal of the transistor, you can basically come up with three different transistor configurations: common base, common emitter, and common collector. So for this, the rest of the discussion, we stick into this common emitter model, because this is very common configuration in most of the transistor circuit. So this common base and common collector can be rarely found, but again there are some certain specific applications for common base and common collector configuration. But we'll discuss and we'll move forward with common emitter configuration, which is commonly used in most of the transistor circuit. So from here onward, so here our discussion is limited to common emitter configuration. So the analysis and everything is very similar to this common emitter configuration for both other cases. So you don't need to worry too much, but for the discussion and the selection of examples, we basically focus on common emitter configuration. So the calculation is pretty much same for other cases as well. So in that common emitter configuration, if I select a NPN type transistor, so this is the arrangement. So this is your emitter, this is your collector, this is your base. Okay. So then from this previous figure, we found that this is your input circuit. So this is your input circuit. This is your output circuit. Okay. So then what are the parameters which we can discuss to show the performance of your input circuit? So these are the parameters. So one is VBE, voltage between the base emitter junction, or the voltage at base with respect to emitter. Or as you can simply say that the junction voltage between base and emitter. This is all, always in forward bias, because we discussed this. So to make this active, we have to make this base emitter junction forward bias all the time. So that base emitter junction is a kind of a forward bias tap. So the characteristic of this base emitter junction would be very similar to a diode characteristic, which is basically in forward bias region. At the same time, the other parameter is the base current, IB. So then you can basically explain the behavior so happening in this input circuit using these two parameters, IB and VBE. Okay. So then your input circuit for the common emitter configuration is basically a base emitter junction. So you can explain the behavior of the input circuit by two parameters. One is the base current, the other one is the base emitter junction voltage. Similarly, for the output circuit, so you have two quantities. So one is actually collector current. So the output circuit is simply in between collector emitter junction. So you can basically describe the output circuit and the behavior for that in that output circuit using these two parameters, IC, VCE. Okay. So keep in mind, for common emitter configuration, this is your input circuit, and Base current and base emitter voltage basically characterized your input circuit. Similarly, collector current and the collector emitter voltage simply characterize the output circuit of the common emitter configuration. Okay, done. So then we'll see how we can power the transistor. So this is already discussed, but for this particular configuration, how we can manage it. So this is the base, this is the emitter, this is the color. So you can connect two sources for the input side. So this is your input circuit and this is your output circuit. So you can connect two sources to the input and output to make this base emitter junction forward bias and base collector junction reverse bias. So how do you do it? So this is your base emitter junction. So you know that this is the NPN transistor. So this is N, this is P, and this is N. So these are the semiconductor materials which we connect to NPN. So to make this base emitter junction, so there is a junction diode like this. So to make it forward bias, you have to simply connect a source with the positive polarity. So I'll connect a source of VB in that fashion. So then this base emitter junction is simply forward bias. So we have another diode in between base collector junction. It's again something like that. So then we need to make this base collector junction reverse bias. Not this junction collector emitter. So you need to make the base collector junction reverse bias. This junction. But you can connect a source to this collector emitter circuit. How do you make it reverse bias? So this is a negative terminal of the diode. So if you basically connect negative positive terminal for this, so then ideally this diode should be reverse bias if you basically apply a positive voltage to the base. So I will assume that this is the way we can supply or connect the voltage source like plus and minus. So here we have a negative terminal of the diode which is basically connected to the positive terminal of the diode. So then we need to clarify that this base collector junction is reverse bias due to this applied voltage of VC. So how do you verify that whether it's reverse or not? So we'll mark the voltage drop. This is your voltage drop VD across this B and C. So how do you do? So if you apply Kirchhoff law for this outer loop, which is basically covering this base collector junction, apply Kirchhoff voltage law covering base collector junction. So we have VD plus VC equals VB. So from here we can simply claim that VD equals VB minus VC. VD equals VB minus VC. So then to make base collector junction reverse bias VD should be less than 0. So if you substitute this, VB minus VC should be less than 0. So then VB should be less than VC. So then for this common emitter configuration, if you power up the transistor using two sources, one is basically connected to your input side, input circuit. The other one is basically connected to your output circuit. So to make it forward bias P-base emitter junction, you can easily connect this VB source to this way. Then definitely this base emitter junction get forward bias. So then to make this base collector junction for reverse bias, so you can connect a kind of a external source VC to the circuit from this output side, but the value of the VC should be greater than VB. Otherwise, your base collector junction will not be reverse bias. So if you basically maintain this condition for this common emitter model, you can basically manage this base emitter junction forward bias and base collector junction reverse bias. So by connecting the sources in that way to the input and output circuit, so you can basically manage the two conditions, base emitter junction forward bias and base collector junction reverse bias, for this common emitter circuit configuration. Okay, so this is the way you can power the simple common emitter configuration using external sources. Again, still we are with two sources. So later on we can see like how we can reduce it to the single source, but there's a kind of a condition we need to maintain. Whatever the voltage you feed to the base should be less than compared to the voltage at the collector. So then by keeping that condition in our mind, we can move it to the single source, because otherwise we cannot get your base collector junction reverse bias. To make this particular junction reverse bias, so you have to apply a voltage to the base, which is exactly less, which is pretty much less than the collector voltage. So if you maintain that condition, you can basically make your transistor active by pushing your base emitter junction to forward bias and base collector junction reverse bias. So this is the simple summary of this common emitter configuration. Okay. So at the same time, we discuss this point. So if you want to characterize your input, so these are the two quantities you want to get involved. If you want to characterize your output, so you should be able to get some characteristic information with respect to IC and VC. So the input for this common emitter configuration, your input circuit basically characterized by IB and VBE, base emitter junction voltage and base current, and your output is basically characterized using this collector current and collector emitter voltage. So keep in mind those information. So then we will move to the next. How do we solve a circuit? Very simple circuit. So I am referring this exercise 1 in the slide set, EX1. So you have a circuit like this. So this VBB equals 3 volt, RB equals 10 kilo ohm, RC equals 1 kilo ohm. This is 20 volt. Okay, this is the simple circuit with two different power sources. So see, like your VBB is 3 volt and VCC is 20 volt. So from the previous discussion, we basically claim that VB or VBB basically less than VCC. Otherwise, your base collector to make base collector junction forward. Sorry, reverse bias. So it's there. So you have 3 volt connected to the base and 20 volt connected to the collector. So we have two resistors basically connected to the base to limit the current, RB and RC. One is 10 kilo ohm, the other one is 1 kilo ohm. So you are asked to evaluate these quantities: IB, base current; IC, collector current; IE, emitter current; VB, base voltage; VC, collector voltage when this beta equals 50. So the only information given here is this beta, DC current gain is 50. Other than that, in this diagram, it shows that the voltages of the supplies, the 3 and 20, and we have 10K and 1K in the base and collector. So we need to evaluate these quantities. So previously we identified two circuits. So one is the input circuit. So the other one is the output circuit. So now we have two circuits. One is the input circuit. The other one is the output circuit. So we have two more relationships. IE equals IC plus IB. IC equals beta times IB. So these are well-known expressions you can use anytime. And other than these two equations, rest of the equations are circuit specific. So it's depend on the circuits which you are referring. So you can use Kirchhoff current law, voltage law, and you can apply those fundamental formulas for input circuit and output circuit to evaluate input and output separately. Okay, so we'll see how we can move forward. Okay, so we basically identify two circuits. One is the input circuit, which basically include this base emitter junction. So this is base, so this is base, this is emitter, this is collector. So the one circuit is basically your input circuit, including this base emitter junction. So the other one is this collector emitter circuit, including this collector emitter junction. So we'll apply Kirchhoff voltage law, Kirchhoff voltage law for the mesh for this input circuit, including base emitter junction. So we'll apply Kirchhoff voltage law for the input circuit, including base emitter junction. So then we can mark this base emitter voltage VBE. So the arrow directs the point where we need to specify the voltage. Now this arrow is pointing to the base. So it means we are referring the base voltage, but with respect to emitter. So we are referring the base voltage with respect to emitter. So the arrow should be from emitter to base. So keep in mind. So the arrow is like this, base emitter. Okay. So if you apply this Kirchhoff voltage law, so and mark these currents as well. So this is your base current, IB. This is the emitter current, IE. So this is the collector current, IC. So keep in mind all the time these IB, IC and IE are current flow into these particular terminals. Okay. If you so once you mark this current very precisely, keep in mind, so those are the current flow into the particular node. So this is your collector, this is your emitter, this is your base. Okay, for example, if you have this kind of a circuit, so this is like supply voltage. So this is your collector current, not this one. This is something else. This is your base current. So this is your collector current. This is the base current, not this one. This is something else. So that's why I ask you, I'm like, so you have to be more precise once you mark these currents and voltages. Sometimes whatever the current you mark in the circuit may exactly not be the collector current or base current or emitter current. So keep in mind. So identify the nodes of this transistor or the terminals of this transistor and mark the current which is basically close to these terminals. So then you don't may get confused. Like for example, if you mark your collector current here, it's not the exact collector current. So that's why. So this is your collector. So mark the collector current which is close to this collector. This is your base. So mark it very close to this node. So then we can avoid this misleading this parameter. So this is base emitter junction voltage, base current, collector current. So this is again this VCE, the voltage at collector with respect to emitter. So we'll apply Kirchhoff voltage law for this input circuit including base emitter junction. So VBE, this voltage, and we have this base current flow from this direction. So then the drop across this resistor would be like this. This is the drop RB into IB equals VB. Okay. So I just apply Kirchhoff voltage for the input circuit, including this base emitter junction. VBE plus RB IB equals VBB. So, and again we know that to make this transistor active, to make this BJT active, we need to make base emitter junction forward bias. So if we consider this diode model, dual diode model, there is a diode in between this base emitter. So you have this kind of a diode here. So then to make this diode forward bias, we need to apply a voltage which is at least greater than or equals to 0.7. If it is, these p-n types are basically gain from silicon. So then if this junction voltage, this diode is forward bias, we know that if the diode is forward bias, there is a kind of a 0.7 volt drop across this diode. If we stick into the simplified model, we can think of like once your diode is forward bias, there should be at least 0.7 voltage drop across this diode. Otherwise, it's not get forward bias. Once it is forward bias, there's a, so you can simply replace this diode with a fixed DC source of 0.7 volt. So then we can assume that VBE is basically equals to 0.7 volt due to this forward bias that between B and E, base and emitter. So then substitute those values. EB is 0.7, RB is 10K, IB, VBB 3. So you can easily find IB 3 minus 0.7 divided by 10K. So this is somewhere around 0.23 milliamperes. Okay. So then this base current is 0.23 milliamperes. So if you argue in the other way around, if you want to maintain a base current of 0.23 milliamperes, what's the resistor you need to place into the base is 10K. Okay. So if you are arguing the other way, if you want to maintain this much of base current, you need to connect a 10K resistor to the base. Now this particular calculation shows something else. So we are given that these resistors are there and ask us to calculate the base current. So then we follow this simple Kirchhoff voltage law and get that base current as 0.23 milliamperes. So similarly, we can argue into the other way. And if you want to maintain a 0.23 milliampere current flow through the base, we need to basically connect a 10K resistor, 10 kilo ohm resistor to the base. Okay. So now this is your base current. And this HFE or the beta is given as 50. So beta is given as 50. So then if you know the base current, you can immediately calculate the correct current as beta IB, which is equals to 11.5 milliamperes. Okay. Now you know the collector current as well. So base is done, collect is done. So your emitter is again can be evaluated very easily. So this is 11.77. So these are by standard equation which you can use anywhere in the transistor. But this expression, this is unique for for the circuit. So other than these two expressions, you can get two more equations by applying Kirchhoff voltage law, current law to this input circuit and output circuit. Okay. So keep in mind this analysis is very straightforward. So you have two equations in your hand. One is this IE equals IC plus IB. So the other one is IC equals beta times IB. So those two equations are there in your hand. Other than that, you can take or you can get two more equations by applying Kirchhoff voltage law most of the time. But there may be certain cases you can apply Kirchhoff current law. Two more equations by applying Kirchhoff voltage law mainly to the input circuit and output circuit. So we can easily get four equations. Two are standard they are in the transistor circuit. So the rest of the two you can easily get through Kirchhoff voltage law by applying for the input and output circuits. So this is very straightforward. So nothing to worry, but to apply these Kirchhoff voltage laws, you have to first mark the currents, DC current precisely, and you need to mark the respective voltages precisely. So otherwise, whatever the Kirchhoff voltage law output would be completely wrong. So before applying Kirchhoff laws, so you have to precisely mark the voltage drops and current flows, basically directions of those current flows and voltage. So then you can take two equations by applying Kirchhoff voltage law to the input circuit and output circuit. In addition, you have two equations in your hand, which is IE equals IC plus IB and IC equals beta IB. Okay, so then this is done now. So we'll move to the next set of parameters we need to evaluate. Okay, now we need to evaluate VB. Find VB. So this is actually the voltage at base. So while going through this calculation, we found that VBE equals 0.7. So which means VB minus VE is 0.7. What about the voltage at emitter? So this is basically ground here. So this is basically ground here. So it means VE equals 0. So this is already ground. So if this VE is 0, so then definitely your base voltage would be 0.7. Now we found this one also. So how do you find VC? So to obtain VC, we need another equation which contains voltage at collector. So for that, we can apply Kirchhoff voltage law. Kirchhoff voltage law for the output circuit, including collector emitter junction. So very simple. So just apply Kirchhoff voltage law. PCE. So the collector current flow into the node. So then this become plus and this become minus, plus ICRC, they drop across this RC resistor, which, which is equals to 20, which is equals to VCC. VCE plus IC, so we found it previously. So IC equals 11.5, I guess, milliampere into RC is 1 kilo ohm equals 20. So then you can easily get VCE. VCE is actually 8.58. So we did a simple thing. We apply Kirchhoff voltage law for the output circuit including collector emitter junction. So then we can bring this collector into the equation. So then we once you apply Kirchhoff voltage law, VCE plus ICRC equals VCC. So you can easily find the voltage of collector with respect to C. So using this knowledge, the emitter voltage is 0. We can simply claim that the collector voltage is equals to VC is equals to 8.5 VE equals 0. Done. Okay, so this is the way we analyze this circuit, as I highlighted before. So we have two equations in your hand. One is IE equals IC plus IB. So the other one is IC equals beta times IB. So those are by default. So other than that, you can basically take at least two equations. So by applying Kirchhoff voltage law for the input circuit and output circuit. Yeah, okay, so so anyway, like I am recording this session and I'll share it to you, so you can, so don't worry. Yes, okay. So then other than these two equations, you can simply borrow two equations by applying Kirchhoff voltage law for the input circuit and output circuit. So then with these four equations, you can do whatever. So here, all these resistors and sources are given and you are asked to evaluate the currents and voltages. But in practical scenario, this may be the other way around. So you have to select the transistor. So once you select the transistor, you know this beta value of the transistor. So you have comprehensive idea about the transistor. What are the operating regions? What are the maximum currents and voltages this particular transistor can handle? So everything should be there, how this transistor affects with the temperature and everything. So in addition to that, you can basically get this information, beta value, easily from the data sheet. So then if you basically design this VBB and VCC based on the transistor parameters. For example, let's think of like, so in the transistor data sheet is given that VCE max equals 25 volt. So just think of, so in the transistor data sheet, it's given that VCE max equals 25 volt. So what's this VCE? So this is VCE. This is your VCE. So it means for this particular circuit, now you have idea about what kind of a circuits you are implementing. So you are planning to include a collector resistor. And so what would be this VCC? So what would be the value of VCC? So VCE max is 25. Now you have to decide what would be the VCC. Let's assume I use a VCC of 35 volt. Can you do it? Yes. Because how do you manage to do it? So you can place 25 volt here. So you can basically place this 25 volt here and rest of the 10 volt across this RC. But keep in mind, if your system is not working properly, so for example, unfortunately you manage to so there may be a kind of a short circuit path created across RC. So then the 35 voltage apply across this VCE junction. So but it can tolerate up to maximum 25 volts. So once you apply 35 volt without this RC, so this transistor get burned. So for the safe side, what we can stick into is, so we can select our source to that level, which is aligned with this VCE max. So then without this RC, if you just directly connect the source of 25 volt, so this transistor can manage this collect emitter junction voltage up to 25. If you use a higher voltage source, keep in mind you have to maintain this RC properly. If not, so then there may be a chance of getting this transistor burned. So that's why I want to emphasize here. So you can think of lot of things. You can decide lot of things by going through the data sheet. So what would be the supply voltages? What would be the biasing level? Where we can place this transistor? What's the impact of the temperatures and how do we manage the temperature? For certain transistors, we have to manage the temperature, and sometimes you may need a heat sink to regulate the temperature. So there may be a lot of issues. So in this for the heat sink, so you have to design the heat sink as well by looking at the what kind of heat is basically generate through this transistor. So you have to absorb that much of heat, or you have to transfer this heat of the transistor to the heat sink. So likewise, you can think of a lot of information by looking at or going through this data sheet. But these are very simple information, you can pick it other than this beta value. So let's assume you basically identify the sources accordingly. So then your beta is known for the given transistor. So then if I ask you to make your transistor operate at base current of 0.23 milliamperes, what would be the base resistor you need to connect? So you can do the same calculation into the backward direction and simply claim that we need to put 10 kilo ohm resistor to the base to manage 0.23 milliampere current through the base for the source of 3 volts and 20 volts. So it means once you connect a 10 kilo ohm resistor to the base, ideally it generated 0.23 milliampere base current. But certain cases, so sometimes we cannot find this 10K resistor. For example, if you calculate and see like you need to 10.2 kilo ohm resistor as RB. So for certain cases, you cannot find the exact combination of these resistors given the calculated value. So then what we can simply do is we can select an approximate resistor value which can easily be purchased in the country. So you can go to the electronic shop and ask like, do you have 10.2 kilo? No. So then what's the available next value? So we have 10 kilo. Okay. So you can just purchase it. And once you plug it to this, you know that there is a 200 ohm loss there. So then what happens is, whatever the current actually flow through this base is slightly above than this one. So then keep in mind, so by practically implementing these circuits, whether we analyze and come up to a certain set of values, once you come to the practical level implementation, so you may choose different approximations for these resistors. So then the exact operating point of the transistor may not be the same as in the calculation. So here I need to highlight 2 points. One is you can back calculate and find the resistors which we require to make these base currents and collector currents. At the same time, the other thing is like, so if you calculate and come across with this certain set of value set and which may not be practically implemented, so you can go for approximation and you can implement a circuit. So then with this approximated resistor values, whatever the analytical values you obtain may not be the exact values or the exact currents and voltages flow across this network. So then your operating point in your paper is completely or slightly different than the actual operating point of the circuit. So those are the two things which I need to highlight in this particular example. Yeah. So next time we'll move to this operating regions and this biasing of a transistor and DC load line and so on up today. So we can wind up the session. If you don't have any questions, if you have any questions, you can just drop a message to the chat box so we can have a couple of minutes time. If you don't have, we can move to the next topic next Monday. Okay, so then have a nice day. Thank you.